Welcome to Homework Lib.
Okay, here we have a layer of a film of titanium dioxide, right? And above a glass surface, refractive index of titanium and glass are given. The thickness of titanium dioxide is given 1036 nanometers, and a light of wavelength lambda equals to 520 nanometers directly falls upon the surface of TiO2. So we want that the reflected lights get cancelled with each other. So what should be the minimum thickness of titanium dioxide? So in this case, the light that gets reflected from the top surface of uh, TiO2 gets reflected from a rarer medium to from a denser medium, right? Because the light was traveling from a rarer medium, so when it reflects back, it reflected from a denser medium. So there is a change of phase by pi, and as it goes down here, then it gets reflected from glass. Now if you compare the refractive indices of glass and titanium dioxide, then the glass is rarer medium, right? So for the glass, since it is reflected from a rarer medium, there is no change of phase, right? So at the top surface, upper surface, we have change in phase, change in phase by pi, right? And lower surface, no change in phase. So what we have to do is use the equation 35.18 that says that for the destructive interference, because we need to cancel, so for the destructive interference we need to hold this condition that 2t should be equal to some integer times the wavelength in titanium, lambda t. All right, so the thickness of the glass should be what? M times lambda t by 2. Now lambda t is the wavelength of light inside the titanium. So titanium is denser, so the wavelength, actual wavelength, and decreases. So titanium decreases by a factor of refractive index of titanium. So this is equal to 520. Right. Let me write this in nanometers upon what is the refractive index? 2.62. So this gives me new wavelength inside the titanium would be 198.47 nanometers, right? This implies for m equal to 1, this is the least possible value of t equal to lambda t by 2. So this is equal to how much? 198.47 divided by 2 gives me 99.23 nanometers, right? But we want to increase the thickness of titanium dioxide, not decrease it. So if we want to increase it, so it should be more than 1036, right? It should be more than 1036. So if we do just trial, then for m is equal to 11, then the thickness would be 11 times 99.23. So this is just above 1026, and this comes out to be how much? 1091.6 nanometers, right? So the increment would be the thickness that we would have to increase. That is what the question is asking us, right? In part A of the question, the minimum thickness that we must add. So increment should be equal to 1091.6 minus 1036, which is equal to 55.6 nanometers. Now, with this adjustment, what is the path difference? Now the path difference would be just twice the thickness, right? Because the light has to come here, then get back. So the extra path that the second wave travels is 2 times the thickness. So path difference is equal to 2 times thickness. Now new thickness was 1091. So 2 times 1091.6 nanometers. So this gives me 2183.2 nanometers, right? Okay, and what else? Okay, so we also want this path difference in terms of the wavelength, right? This is for I. So if we want this in terms of wavelengths, then this is equal to 2183. What was our new wavelength? New wavelength of light in titanium was 198, right? 198.47. So this implies path difference is equal to 11 times the wavelength in titanium. This ends the solution for this question. Thank you for watching.